Welcome to Hot Chips 2024. Session 4, AI Processors, Part 2.
Good afternoon. Welcome to session number 4 today. This is the AI Processors Part 2. I'm Dave Weaver with Akiana, and I'm the session chair for this session. Our first speaker today is Roman Kaplan. Roman is the lead performance architect at Intel, is it Habana or Habana? Habana. Intel Habana. Roman is in charge of setting the performance targets, guiding the software teams on target attainment, and architecting the hardware-software co-designed optimizations. Roman has worked on all of Habana's Gaudi products. Today, in addition to working on Gaudi 3, he works on Falcon Shores, which is Intel's next-generation GPU-based AI accelerator. Please help me welcome Roman Kaplan.
Okay. Thanks, Dave. So, hi, everyone. So, I'll be presenting to you Gaudi 3, which is Intel's latest AI accelerator. So, Gaudi 3 is the third in the Gaudi product line. See, gen by gen significant increase in compute and HBM capacity and peak HBM bandwidth. Today, we reach almost 18 or a bit more than 1,800 teraflops for BF16 and FP8 compute. We have two main SKUs, 900 watts and 1,200 watts with air and liquid cooling. HBM capacity of the latest Gaudi 3 is 128 gigabytes, reaching almost 3.7 terabytes per second of HBM bandwidth, with a PCIe bidirectional bandwidth of 128 gigabytes per second peak. And we also have an embedded NIC bandwidth, total of 9.6 terabits per second bidirectional. That's just the high-level parameters. Gaudi 3 was manufactured with 5-nanometer node process. Moving on, so the main product is an OAM model. It contains 2 compute dies, which we see in the middle of the screen. There are 8 HBM2E stacks, 4 at the top and 4 at the bottom. There's a PCIe Gen 5, 16 lanes, and 24 NIC ports of 200 gigabit Ethernet over Rocky. In total, the total die is composed of 8 matrix multiplication units, which is the MME units, matrix multiplication engine. There are 64 tensor processing cores in short TPC. More on that later on. Total compute T-flops of the vector unit is almost 29 T-flops for BF16, twice that for FP8. The on-die SRAM capacity is 96 megabytes, which is cache managed. The maximum on-die cache bandwidth is 12.8 terabytes per second for reads, half of that for write. And there are also media engines with a rotator and 14 decoders of various types. So the two in the illustration on the right-hand side, the 2 dies are illustrated as the top and the bottom, and with the 2 dies being a mirror image of each other. One step deeper into the architecture, so there's a uniform memory mapping of the HBM by a memory management unit. The entire compute of the chip is clustered into 4 deep learning cores, D-cores. In short, each D-core contains 2 matrix multiplication engines, MMEs, 16 TPCs, and 24 megabytes of cache. There are L2 and L3 caches, which are logically determined. The L2 cache can be used if you allocate data locally in the D-core cache, so which logically serves as an L2. You can also allocate data in each of the D-cores and will be uniformly distributed, and each of the decodes can access this data, and logically this will be used as an L3 cache. The chip also has a separate control block and a separate NOC fabric, and more on that later on. I didn't mention all the details that were already mentioned in the previous slides. Moving forward. Now, the main workhorse of the chip is the matrix multiplication engine, MME. It does all the operations that can be translated to a matrix multiplication. It is a configurable, not a programmable engine, meaning that you don't have any piece of code that's running on this engine. There is a fixed set of registers that control the operation of this unit, and according to these values, this unit just works. Each MME unit is basically a large output stationary systolic array. It is structured in 256 rows and 256 columns, so that's a very big unit. It contains, each internal processing element contains an FP32 accumulator, and a single MME can provide 64K max per cycle for FP8 and BF16 input data types. The MME has an internal block, pipelining blocks that allow it to maximize the compute throughput. So in parallel, if we look at a single long task, this task can be split to multiple smaller jobs. Each job can run independently on the internal blocks of the MME. So in parallel, we can have reading the input of the next job, forming the compute of the current job, and if the output is ready, then writing the output of the previous job. All of them running in parallel. This allows us to maximize the throughput and reach very high compute utilization by the MME, meaning we eliminate idle times of the compute with this pipelining structure. There's also an integrated transpose engine, transposing on the fly the inputs to the compute engine. And transpose operations, as you know, come very handy in deep learning. And the accumulated results, once they're ready, can be converted to any output data type within the MME. It's part of this internal pipeline. So the output that is written, the cache or HBM, is already in the data type that we want, BF16, FP8, or whatever. There are also internal buffers that contain the inputs that were read, and they can be reused. So these buffers are large, pretty large. There are several hundreds of kilobytes in size, and then they are replacing the L1 cache. So if we read some part of an input and we have large matrix multiplication to perform, the same input can be used for many parts of this matrix multiplication. The ME also contains an integrated address generation unit. So this address generation unit allows us to access data in a notation of 5-dimensional tensors like the way we use in AI and deep learning. The AGU also contains read padding, which is very necessary for convolutions, for example, whenever we have to pad parts of the input in the compute. Also have out-of-bounds write prevention. The tensor processing core, the TPC, total of 64 such units on the chip. They execute basically all operations that are non-matrix multiplications. So we have much lower compute capacity for the TPC, and therefore any vector operation is running on TPC, the rest is on the MME. TPC is a programmable unit. It's programmable with C, and that is enhanced with TPC intrinsics. So TPC, the intrinsics allow us to support the additional operations the TPC has over just a regular CPU. So TPC is composed of a VLIW with 4 separate pipeline slots. First main slot is the vector slot. It is a 256 bytes wide SIMD, split according to the data type. If it's 1 byte, so 256 elements in parallel, 2 bytes data type like BF16, 128 elements in parallel, and so on. We have also a scalar pipe, load pipe, and a store pipe. All of these pipes can run in parallel, which means that whenever we perform some operation, some compute operation in the vector pipe, we can load the next input for the vector pipe, or we can store in parallel the previously computed output. The load and store slots also integrate an address generation unit, and the address generation unit allows us to calculate the access addresses, again, with a 5-dimensional tensor notation, just like the MME. So logically, the software is working in tensor notations, which is very useful and easier to manage. TPC supports calculation of all the 1, 2, and 4 main data types, floating point and integer. I didn't write them down here, but I think you can, you all know, imagine which they are. Each TPC also has a 12 kilobyte of a vector register file and an 80 kilobyte of a vector local memory, which is used as a scratchpad to store some intermediate results if needed. The TPC also integrates a latency hiding mechanism, so inputs can be prefetched ahead of time, and before the execution initiates, which we will see in a moment when we want execution to initiate, when we want to schedule that, and this latency hiding mechanism allows us to avoid waiting all the longer latencies of accessing data from the lower memory hierarchies like the HBM. Memory subsystem. So the memory subsystem has a unified memory space for the cache hierarchies and the HBM. We integrated a near memory compute, which allows us to do add and sub operations and max or min. The add operation, for example, is very handy for collective operations or networking. And it also can save some of the work for the TPC in the simple operations, some of the residual add that we have in language models. There's a usage of a memory context ID to tag cache lines or groups of cache lines with some shared algorithmic usage. For example, if they belong to the same input tensor or output tensor, I'll explain in a moment why we need that. There are cache directives that allow us for every cache line to decide programmatically in the software to decide whether this cache line will not be, or we will just read it from the HBM and we will not cache it, or we will cache it in the L2, meaning locally in the D core, L3 uniformly distributed across all the cores, or L2 plus L3. There are also cache directives that allow us to discard data, meaning that we take cache lines with the same MCID and we just invalidate them in the cache. That is very useful in inference workloads. Wherever we have intermediate activations which do not need to be stored for later on, we can just discard them or invalidate them once they are consumed by the engines. There's also a degrade cache directive that allows us to reduce the hit count, or you can say the priority of data within the cache. And this is also can be used for cache lines with the same MCID. The degrade directive is very useful for training workloads. Wherever we have some activations that we want to store for the backpropagation, for example, we don't want to invalidate them. We want them to be left valid for the backpropagation. And we will be happy for them to stick in the cache in case someone or some operation will need to read them. Looking at the control path and runtime driver, so then the control path has a separate NOC fabric that allows, or it is used only for control path messages. A sync manager is the control block that handles all the necessary control logic. It dispatches work to the designated units, meaning engines, usually it's the engines, MME, TPC, or NIC. And it also waits on counted events, on number of events that need to finish, and then it can trigger the start of a new job. For example, if we want all MMEs to finish doing one task, and then we want to initiate the TPC to perform the task with the output of the MME, the sync manager does that. The runtime driver sets the engine's dependencies by configuring the sync manager. So the runtime driver just writes to the sync manager what are the dependencies. The dependencies themselves are decided in a higher software level. We'll go to that in the next slides. Well, the runtime driver also submits jobs through a submission queue and receives completions through a completion queue. And there's an interrupt manager that enables passing event asynchronously to the driver. So getting the completions or submitting the works can be done asynchronously without any interrupts. the Intel Gaudi software suite. So it integrates, though, the Gaudi software suite integrates the main frameworks that are used today. It means we have deep spin integration, LM serving for VLLM, TGI, these are the latest known ones. There's also quantization support. There's support for quantizing, mostly for 2-byte BF16 or FP16 to an FPA data type. The main layers, or main proprietary software layers, are first, which is, and one of the most important ones, is the graph compiler. The graph compiler determines all the engine's dependencies, on the engine dependencies, and it sets or it determines what is the control logic that is needed to execute the engines in the right order. There's also a software layer that is handling the matrix operations. Basically, it decides how to configure the MME properly and efficiently. There's also a collection of TPC kernels, and there's a collective communications library, HCL in short, that contains all the networking operations. For the TPC kernels, there are several sources. So first is there's the Habana optimized TPC kernel library. So that's a kernels library, a large collection of the main kernels that are being used in deep learning and generative AI. There are also custom user kernels. So any user that is using the system can write his own or her own kernels. And there are also MLIR-based fuse kernels, which are generated on the fly during graph compilation. So if there is a sequence of operation, for example, element-wise multiplication, addition, subtraction, that can all be executing serially in one program, in one piece of code, and at the moment they are not, the MLIR fuser automatically detects this kind of sequences and fuses them to a single automatically generated code section. This MLIR fuser significantly reduces the bandwidth that is required for executing such kernels, and also the runtime. How all these components work together. So if we look at the diagram on the right, there's a simple execution subgraph. There's a gem, general matrix multiplication operation, and a vector operation that follows that. The output of the gem is the input for the vector operation. That's on the top part of the illustration. If we naively schedule the two, we'll have the gem running from start to end, finishing its execution, writing the outputs to cache. Due to capacity conflicts, some of the outputs will be evacuated to HBM. Then the vector unit starts its own execution, reading some of the inputs from HBM, which take long latency, maybe potentially reading some of the inputs from cache. Also, the runtime is long because they are not running in parallel. Each run is run serially. If we look at a more efficient execution at the bottom part of the illustration, then we'll take large execution tasks and we split it to smaller slices of execution. Each slice is independent of the other slice. Within each slice, we use the subgraph relation, and we execute the engines with a producer-consumer such that the producer writes its output to a very high memory hierarchy, L2 or L3 cache, and then the consumer, in this case, the TPC, the vector operation, reads the input from a high memory hierarchy in high bandwidth. So the graph compiler is the software layer that is responsible for scheduling this kind of work, deciding all the dependencies and finding this kind of pipelining and slicing opportunities. So determining the slice size is a very hard operation. It requires a delicate balance between high compute utilization. We want everyone to achieve high compute efficiency with their machine. So you want the work chunks to be large enough to utilize the compute engines well. But on the other hand, you have some fixed cache capacity you want to fit in with this producer-consumer relation. So you have some limit for the size of the slice. You also want to maximize the engine parallelism. So it means the tail and head tasks that we see at the bottom part, we want them to be as small as possible to maximize the parallelism. And therefore, we want to make slices as small as possible. And the graph compiler is the software layer that does this very fine-tuned and very detailed balancing. The NOC fabric was designed from first principle, or as a main principle, to support this kind of parallelism. So the bandwidths that both the MME and TPC consume and produce can be sustained by the NOC fabric by design. So networking, all the networking ports are exposed as NICs to the driver. NICs are activated with RDMA verbs over device virtual space, and collective operations can be executing with low overhead because of the efficient control block and efficient control fabric that I just presented. A single Habana Lab server HLS3 node contains usually 2 host CPUs, Intel Xeon CPUs, 8 Gaudi 3 OEM cards. The cards are connected with a peer-to-peer connection between each card, and there are also NICs that are connected for scale out. So the same from all the NICs that the Gaudi has, some are used for scale up and some are used for scale out. The 24 NICs are distributed equally between the scale up and scale out, meaning that out of the 24 ports, 3 are used for scale out. The remaining 21 ports are equally split between the remaining 7 neighbors that each card has. So peer-to-peer connection bandwidth and scale out bandwidth are the same from each card to each card. With this kind of connectivity, there is no need for a switch inside the node to support scale out. Just only the cards are enough. If we look at the total scale up bandwidth, bidirectional bandwidth that this connectivity allows, it allows 67 terabits per second, and there's also a scale out bandwidth of 9.6 terabits per second bidirectional. Now the interesting part, so we measure the performance on a current version of the Habana, no, the Gaudi software suite. All the benchmarks that we see here are generative AI, large language models, done with FP8 precision. This is an intermediate version, so it's not a measurement of a release or of the Gaudi software suite, but it is preliminary results which we expect to improve. The 1.18 software release, which will come out in September, will also contain these benchmarks and more. We see if we compare Gaudi 3 to Gaudi 2, we see gen over gen improvement of almost 3x. This is an improvement not only due to the 1.5x larger HBM bandwidth of Gaudi 3 versus Gaudi 2, but also due to the larger HBM capacity, which we can use or utilize here in the inference. Today, Gaudi supports all the main LLM models and generative AI models, and they are functional on Gaudi 3, and software efforts for improvements and optimizations of performance are continuously improving, and we work on large variety of use cases to improve even further most of the results we see here. So Gaudi 3 provides acceleration, AI acceleration at any scale. There's a close collaboration between the hardware and software teams, even today, to reach as high performance as we can and to deal with the new ways that the software is needed to reach high compute utilization on the Gaudi. The software stack is continuously improving both performance and expanding the functionality to support every new framework or every new requirement. Gaudi 3 allows us to provide acceleration at any scale. So from a single card level to a node to a full rack and up to a full cluster. And there are multiple of HLS3 clusters that are being built and designed today. There are more details both on the card level and the scale up, scale out architectures in the white paper. And that's it. Thank you. Questions, please.
Great, thanks, Roman. Okay, we have a question on the Slack channel.
Yes, we do. Can you hear me? Yes, you can. All right, this question is for me. Is your FP8 format a microscaled format or an independent FP8 element?
I will need to check these details. As far as I know, it is not an independent format. It is something that is well known. Yeah, standard.
Standard microscale
So-
shared element. Okay, thank you. This is from Robert Williams, the white paper for Gaudi listed a 900-watt TDP, the liquid cool variant. Did this change at some point?
No. So we have 900 watts can be used with liquid or air cool. Most of the customers prefer 900 watt with air cooling, but we also allow reach up to 1200 watts with the liquid cooling.
We have a question on the live mic here.
George Kozma from Chips and Cheese. So I know that the Habana software stack is not the same as the One API stack. How are you planning on dealing with that for Falcon Shores, which is replacing Gaudi?
So Falcon Shores will support One API software stack, and the teams are working to have it integrated with the Falcon Shores stack.
And so any programs written for Gaudi 3, will that be forward compatible?
They will be compatible, yes. So we also need to provide a path between the Gaudi software suite and the One API, yes.
Thank you.
Okay. Any more on the Slack channel?
Yes, we do have another one from Juan Lee. Does Gaudi support VLLM inference over Hugging Face TGI server? And if VLLM supported, is page attention supported?
So yes and yes, Gaudi supports VLLM, and the efforts or optimization efforts that I talked about, part of them are improving performance for VLLM. It is already functional and it's working nice performance, but we want to work with good performance.
Okay. Live mic.
Hi, Jeff Smith. Thanks for the great talk. First of all, I want to say I personally enjoy the RDMA NICs on package, which is a nice thing from a lot of system integrator perspective. I wanted to know if you could share anything about the inter-L2 coherence behavior and any consequences on the programmer model for kernels spread across multiple quadrants.
So the idea with the caches, there's 96 megabytes of SRAM. You can use that however you want per data. So if you want a piece of data that is shared across the engines of all decores, you can decide that it is allocated as L3, which means that it's uniformly spread between all the decores. And then all the decores or all the engines can access the data with the same bandwidth uniformly. However, if you want higher bandwidth and you detect that the software detects that only subset of the engines needs this data, then the software will decide to allocate it in the L2, which means that it will be allocated only locally for the decore of the engines that need this data. So it's per usage. So if you have a gem that needs with an input that is used by all MMEs, then you will allocate it as an L3, for example.
If I like the worst case behavior and I have like a single frequent reader, single frequent writer, multiple frequent reader, I want to be broadcasting to all quadrants frequent changes. Is that something that the compiler would just need to put into L3, or is writing to a local L2 going to be disseminated to remote L2s with any hardware accelerated behavior?
So whenever you write it locally, and then when the reader needs to state how it wants the data to be read. The software needs to detect that there are multiple consumers to this data, and therefore it will allocate it in a memory hierarchy that will allow all the readers to access this data. So either only L3 or L2 plus L3.
Thank you.
Thank you.
Do we have another Slack question?
We do. I'm going to paraphrase it slightly. Why do a cache instead of SRAM with data movement to software directed? You just answered most of that. I guess what I'm curious about is, do you have anything besides a pull model for cache loading? Do you have a lot of prefetch control for block moves and prefills?
That's a good question. So there is some support for prefill and prefetch. It should be more delicately managed by the software. If we want to schedule that, we can do it, for example, with a TPC. You can say cache warm-up or prefill cache warm-up. It needs to be scheduled separately. But it requires a separate software flow. I'll also answer the first part of the question, why not do a software managed SRAM? Because of the software complexity. That is why. It is very complex to do an SRAM scratchpad. Gaudi 2 had an SRAM scratchpad. It requires a lot of software scheduling and a lot of software handling in addition to the computer engines. It means there's an additional engine that needs to just shuffle data back and forth through the SRAM. Cache eliminates that.
Thank you.
Thank you.
Are there any further questions right now? Okay, I guess that's it for now. Let's thank Roman.
Thanks, sir.
Well, our next talk in the session is from AMD, and they'll be presenting the AMD Instinct MI300X Generative AI Accelerator and Platform Architecture. We have two speakers for this talk. They'll be sharing the time. The first is Alan Smith, who's an AMD Senior Fellow and Lead Silicon Architect for AMD Instinct GPUs. He specializes in advanced development of system-in-package GPUs for exascale AI and HPC systems. His expertise includes optimizing IP and SoC technologies and architectures across network and chip, memory, and cache architectures for large-scale SoCs. Also tailoring them for energy-efficient GPU-accelerated computing. He also has extensive experience in advanced 2.5D and 3D packaging technologies, balancing performance, product cost, and manufacturing considerations. He's a senior member of IEEE and holds bachelor's and master's degrees in electrical and computer engineering from Georgia Tech. Now, our second speaker is Vamsi Alla. He is a chief engineer at AMD and an AMD fellow. He leads the system deployment of Instinct platforms and accelerators within the DC GPU division. With deep experience in system debug, validation, and optimization, Vamsi has played a pivotal role in the development and deployment of several generations of Instinct products. His work ensures that AMD's high-performance computing solutions meet the rigorous demands of modern data centers and research institutions. As an IEEE senior member, Vamsi is recognized for his contributions to the field of computer engineering, particularly in advancing the capabilities of GPU accelerators. His insights and leadership continue to drive innovation in the industry. Let's welcome Alan and Vamsi.
Good afternoon, and thank you for that introduction. It's my pleasure to be here today to talk to you all about MI300. So in this talk, I will provide an overview of the MI300X architecture and CDNA3 architecture, including the HBM3 memory system and spatial partitioning. I'll then hand the talk over to my colleague Vamsi that he just introduced, who will cover the fourth generation Infinity architecture, system architecture, and survey MI300X platforms and features, and we'll wrap up with some application performance examples. MI300 is the latest iteration of Instinct products built for large-scale accelerated systems. It's the first based on a chiplet architecture for unified compute and builds on the domain-specific architecture of MI100, which allowed for more area and energy to be dedicated to compute, and the multi-chip module architecture of MI200, which enabled scaling beyond the single reticle. There are two versions of MI300. There's MI300X, which is built for AI systems, and MI300A, which is an APU with integrated x86 cores for HPC systems. Both were architected to deliver the highest performance in their class. This presentation will focus on MI300X and its distributed AI systems. Generative AI model performance requires memory capacity and bandwidth, so we targeted the scale of MI300X to meet this need, with a level of integration not possible with a monolithic design. With fourth generation Infinity Fabric, PCI Express Gen 5, HBM3, and CDNA3 architecture, MI300X implements balanced scaling across compute, memory, and I/O subsystems. MI300X is built with 12 chiplets. There's 4 I/O dies and 8 accelerator dies. This image is a top-down view showing the accelerator chiplets on top of the I/O dies. The 4 I/O dies are built in TSMC N6 and are interconnected with Infinity Fabric Advanced Package links. They contain the PCI Express Gen 5 subsystem used to connect MI300X to the host and to the scale-out NIC. They also contain the 4th generation Infinity Fabric links used to scale up to 8 MI300X in the node with 896 gigabytes per second of aggregate bidirectional bandwidth per GPU. The Accelerator Complex Die, or XCD, is built in TSMC N5. Each contains an L2 cache, 4 shader engines with 38 active CDNA3 compute units. Together, the 8 XCDs scale MI300X to 304 active compute units. To define the architecture for CDNA3, we started with the target workloads and systems. In addition to leadership in traditional simulation, we wanted MI300X to be leadership in distributed AI inferencing and training. So we retained the FP64 capabilities of CDNA2 that enabled leadership on top 500 and green 500 lists to power the next generation of supercomputers like El Capitan at Lawrence Livermore National Laboratories. Then we built upon this to integrate the necessary elements to enable leadership AI capabilities. We started with doubling the throughput of the matrix cores, low precision ops, and we added 2 to 4 structured sparsity for the most important inferencing formats. We increased the total number of compute units in MI300X by 1.3x that of MI250X. These changes, along with higher frequency, combined to deliver over 1.3x sparse tensor multiplication speedup over MI250X for the same format. To improve application performance, we added support for co-issuing multiple combinations of vector ALU operators with vector and tensor ALU operators. This allows softmax and matrix multiplication to be parallelized for flash attention and to overlap all reduced with gems. Finally, to deliver leadership AI performance requires state-of-the-art numerical formats. Formats are rapidly evolving, and staying on these trends requires collaboration and planning. AMD has been working with industry partners to develop and standardize the latest formats. The most important of these is FP8, which has become the sweet spot for inferencing and training. And MI300X supports both E5 M2 for greater range and E4 M3 for higher precision, as well as being OCP FP8 interchange compliant. FP8 with sparsity on MI300X delivers greater than 12x speedup over MI250X with FP16. The MI300X 8-stack HBM3 memory system is fully unified and delivers 5.3 terabytes per second of peak bandwidth with 192 gigabytes of capacity. This provides a 1.5x capacity and bandwidth scaling over MI250X. Memory requirements for model size scale with the number of parameters and numerical format, and higher capacity per GPU allows running larger models on MI300X systems. The flagship open source foundational model for Mehta, Llama 3.1, 405 billion parameter, is one such example. Using the FP16 data type for inference, we can fit the entire model on one server powered by 8 AMD Instinct MI300X accelerators. The block diagram of MI300X shows the overall organization and illustrates the 8 XCDs I described previously. The XCD contains a new level of hierarchy, the Accelerator Compute Complex, or XCC. The XCC contains the 38 compute units, L2 cache, and the global resources for virtual memory and work creation. The Infinity Fabric serves as a logical crossbar connecting the XCDs with the Infinity Cache, the HBM, and the external I/O. The memory side AMD Infinity Cache increases power efficiency significantly due to reduced DRAM activity. The Infinity Cache is organized as 2 megabytes per channel, with a total of 256 megabytes for the entire GPU. The XCD L2 caches are kept coherent through a combination of hardware and software-directed thread scope. All atomic read modifier writes can be executed in the GPU Infinity Fabric and support a full suite of floating point atomics. The IO die chiplets are not shown in this diagram, but each hosts 1/4 of these resources. AMD Advanced Packaging and the Infinity Fabric AP links allow the chiplets and memories to function as a single unified device. MI300X introduces multiple CDNA3 compute unit cache optimizations. We doubled the capacity of the L1 data cache to 32 kilobytes by increasing the cache line size to 128 bytes from 64 bytes to increase hit rates and to allow for more efficient use of internal buses. The L1 instruction cache, which is shared by 2 compute units, was doubled to 64 kilobytes to support the higher IPC of MI300X. The 4 megabyte L2 cache increases request coalescing, reduces accesses to the Infinity Fabric, and enables data reuse across the shader engines within an XCD. For example, kernel arguments can be reused after the first wave installs them into the L2 cache by the other waves. As I mentioned previously, the AMD Infinity Cache provides bandwidth amplification and reduced latency for cache hits, minimizing redundant accesses to HBM memory, lowering power, and delivering improved application performance. The XCC hierarchy introduced in MI300X that I previously described was necessary to scale up to over 300 compute units and to facilitate the XCD chiplet construction. Working together, they present MI300X to the programmer as a single unified GPU. At the same time, each XCC contains the necessary resources to function as an independent GPU. Using the same capabilities needed for all the XCCs to work together, smaller groupings of XCCs can be formed to allow MI300X to present as multiple GPUs. We expose these spatial partitions as SRIOV virtual functions, and we protect against a virtual function accessing information or state from another virtual function or the information or state of the physical function. In addition, each virtual function is protected from accesses by the physical function. Memory can be partitioned into multiple NUMA partitions per socket. MI300X supports both 1 and 2 NUMA partitions. We refer to these as NPS1 and NPS4. GPU partitions can be combined with memory partitions to exploit data locality to increase application performance even further. For example, it's possible to run a single inferencing instance of Llama 3.1 8 billion parameter in FP16 on a single XCD partition and accommodate up to 8 parallel instances simultaneously on a single MI300X accelerator. With that, I'd like to turn the presentation over to my colleague Vamsi, who will take you through the AMD Instinct platform.
Thanks, Alan. Good afternoon. I'm incredibly excited to be here to talk about our AMD Instinct platform. Our Instinct platform provides a home for 8 of our AMD InstinctTM accelerators. This allows us to aggregate and provision leadership memory capacity and bandwidth to accelerate generative AI. Our platform also includes 4th generation Infinity Fabric links between the accelerators to provision scale-up and scale-out connectivity. Our platform is built on industry standard design, enabling fast adoption. I'd like to take a minute to go through the platform journey. We've been on a journey of continuous innovation of platform architecture to enable state-of-the-art infrastructure. With MI100, our first major improvement was to add bridge cards between accelerators to extend our Infinity Fabric across GPUs. With MI200, as the power and cooling requirements for accelerators increased, we adopted OCP's OAM form factor to enable them. These are at the heart of the Frontier supercomputer, which is #1 on the top 500 list today. With MI300X, to enable wide adoption, we created a fully contained AI subsystem to serve the needs of LLMs and to make deployment seamless. Let me go through the key attributes of the MI300X Instinct platform. Our Instinct platform is a powerful generative AI computer with up to 10 petaflops of 16-bit performance. The platform enables us to aggregate up to 1.5 terabytes of HBM, as well as provides each accelerator with 896 gigabytes of Infinity Fabric connectivity. The platform brings together 8 MI300Xs in an industry-standard OCP infrastructure. Most host platforms out there already support the OCP infrastructure, making our deployments fast and seamless. Let me go through the high-speed connectivity that our Instinct platform enables. We enable direct connectivity between the OEMs, which provides a simple topology. This enables easy communication collective development. AMD's Infinity Fabric links extend our compute units to do load store accesses to memory across all 8 GPUs. Same links also provide hardware atomic support for synchronization. Each accelerator enables host connectivity by leveraging one PCIe Gen 5 by 16 link. This provisions a fast pipe for host-to-device and device-to-host transfers. The same link can be used by industry-standard NICs to access all 192 gigabytes of HBM per accelerator for RDMA. We've also integrated PCIe retimers in our Instinct platform to make PCI connectivity seamless and easy. Our Instinct platform allows AMD to qualify all the high-speed I/O on the platform, thereby reducing qualification time for our partners. Let me talk through the system management capabilities that our Instinct platform enables. On the Instinct platform, we provision a system management controller which acts as a single point for all system management. This provides a way for data center infrastructure managers to seamlessly integrate our platform. Also, this provides a way to provision discrete CPU and GPU management subsystems, thereby servicing the distinct needs of the CPU and GPU subsystems. All our management is based on open standards like Redfish. For instance, we provide platform security through SPDM measurements and attestation, as well as provide a platform extended root of trust. We've leveraged decades of AMD's experience with data center RAS for our CPU products and brought all that innovation into the Instinct platform. This includes features like full chip ECC memory protection, as well as bad page retirement and bad page avoidance for memory. What this means is large LLM training jobs can run for a longer amount of time without being interrupted. We also leveraged industry standards like Redfish PLDM bundles for firmware management. This allows us to support advanced features like firmware anti-rollback protection, as well as firmware redundancy, where we can automatically detect a bad firmware flash and correct it, thereby increasing data center uptime. One of the main goals of our Instinct platform was to bring a wide variety of partners into the ecosystem. We did this by leveraging Open Compute Project's Universal Baseboard 2.0 infrastructure as the basis for our Instinct platform. This allows for partners to innovate and offer differentiated solutions by customizing various components of the solution, like a distinct host CPU, a distinct storage, as well as network infrastructure. Our Instinct's platform management capabilities also allows our partners to integrate our infrastructure into their solutions, where they can also keep the host system management unique and offer differentiation. A proof point that Instinct platform is a fully contained AI subsystem is seen by the wide variety of partners that have adopted our platform. I'd like to take a minute to talk about our software ecosystem. MI Instinct accelerators and platform are powered by Broadcom, a world-class machine learning software platform. Broadcom is used widely today by some of the best developers in the industry, including Microsoft Azure, Meta, OpenAI, and Hugging Face. Broadcom is available as a PyTorch native backend, has Triton support, as well as support for state-of-the-art attention algorithms. Broadcom is open source, which allows our partners to collaborate and add to the platform, thereby enriching the ecosystem. We've recently added support for open source frameworks like VLLM that allows developers to serve inference models easily. We added support for frameworks like JAX that allow for easy model fine-tuning and training. All this means is supercharged developer productivity for machine learning. As an example, for the wide use of our Broadcom platform is the fact that Meta's Llama 3.1 405B, which is the largest open source foundational model available today, came to market with day zero support for Instinct accelerators through Broadcom. Let me spend a minute on application performance. Combination of our silicon, software, and systems delivers industry-leading generative AI performance on some of the most demanding and popular models. Looking at the performance of a single server containing 8 MI300X accelerators on models like Meta's Llama 370B, we can see that we perform up to 30% better than our competition. Looking at a single GPU performance on models like Mistral 7B, we offer a 20% performance advantage. For training, we wanted to look at models around the size of 30 billion parameters. We think this represents a sweet spot that enterprises are going to use for fine-tuning and training. In such a class of models, our Instinct platform, powered by 8 MI300X accelerators, offers leadership class performance. To summarize, we've looked at AMD Instinct accelerators and platforms, which are widely deployed across multiple hyperscalers and industry partners today. MI Instinct accelerators and APUs offer differentiated architecture for HPC through features like unified memory and for AI with AI-focused data formats. We've also looked at MI300X's memory subsystem, which represents the industry's first 8-stack HBM3 implementation. This enables us to provide 192 gigabytes of memory per MI300X and up to 1.5 terabytes per platform. This enables us to run the largest of LLMs on a single server. We've also looked at AMD Instinct and platform architectures, which are designed on open standards, allow for partner innovation, and provide seamless transition for our end customers. The combination of all of these factors allows for industry-leading AI performance for both inference and training. I'd like to now thank AMD's entire development team, as well as our partners across the ecosystem that have made this product to be possible. Thank you.
Thank you, Vamsi. Do we have a Slack question?
We have a couple of Slack questions. The first one is, your diagrams show the Infinity Fabric leaving the dies in a serial link, or what I assume is a serial link. Is that serial link Infinity Fabric an open standard now? And are other people adopting it, and at what speeds?
Yeah, okay, I could take that one. I was trying to find you. I was like, I know there's somebody reading that question, but yeah, I got you right now. Okay, so the Infinity Fabric on MI300, it is a serial link. They're running at 32 gigabit per second Gen 5 speeds, and they're by 16 links. There are 7 of those links on each MI300X for a fully connected topology between the 8 MI300X accelerators on the node.
So second question related to that. So all of Infinity Fabric transfers to date are going over PCIe Gen 5?
It is the external transporters on PCIe Gen 5 type SerDes. And the second question, I think, was about open standards and so forth. So I think on MI300X, that is not the version of XGMI that is being opened. AMD has talked about Open XGMI, which is now part of the UA Link consortium, and that is in future roadmap products.
Thank you.
Jeff?
Hi, thanks. Enjoyed the talk a lot, and congratulations on the really ambitious project, which seems like it might be the first, enterprise scale active on active stacked chip design. So I actually had a question around that. So one of the long touted benefits towards stacking was, at least I had read, was reduction of lateral data movement across a die.
Mm-hmm.
And the XCD design has the L2 and the system interface along an edge rather than being centrally located, when it doesn't seem like it necessarily had to be. So my question is, were bilaterally symmetric XCD designs considered, or were there bigger benefits towards having centralized kind of back-to-back base die to XCD connectivity?
Yeah, that's a good question. I will say, I'll try to answer what I can. Okay. The considerations for how to interconnect the buses between the XCD and the AID, we did look at several options. There's some considerations on just the current state-of-the-art in GPU architecture and how the construction internal to the shader engines, or the XCC itself that I mentioned, and how data flows from the L2 back into those XCCs. In this generation, it seems like a reasonable choice to support that type of construction where it's more of a folding than a spatial organization between the compute units and the base die. So hopefully that sort of answers your question.
It does. Thank you very much.
Yep.
Have one on Slack?
I do. This is from Christoph Novak. Can partitions be asymmetric? For example, partition from 4 XCDs, one from 2 XCDs, and 2 from single XCD.
Yeah. Okay. So what we support officially in the software stack is what I showed. It's symmetric. The architecture is pretty flexible, but what we support in the actual deployment stacks are symmetric partitions.
Okay, go ahead.
George Kozma from Chips and Cheese. So does each of the 7 Infinity Fabric links to the other MI300X GPUs in the system just sort of a single link to each? And if so, why aren't you feeding into a switch that can then deliver the full 448 gigabytes unidirectional, 896 gigabytes bidirectional to any single GPU?
Yeah, good question. Yeah, they are point-to-point links between each of the GPU pairs within the node. And there are some advantages of not having the additional latency of the switches in the paths, for latency-sensitive transfers in some inferencing workloads. And so in this generation, that was the topology that we chose to go with.
Thank you.
Yep.
Slack?
I do have another from Brian Palmer. Do Infinity Cache or Infinity Fabric support in-memory computing or near data processing, allowing for computations to be performed directly on cached data?
Not in this generation.
Microphone, and please get close to the microphone so everyone can hear you.
Sure, Kevin Creel from Curious Research. Usually I'm pretty loud, so you can usually hear me. So it's interesting to contrast your solution and how you built your chiplets, like 8 chiplets for the compute side and the 4 I/O, compared to both Blackwell and Gaudi 3, which use much larger die, connected only 2 of them per package. What was the trade-off in terms of you have overhead, each of those chiplets have the Infinity Fabric to connect to other, so that's the argument against using smaller chiplets. What was your advantage of using smaller chiplets?
Yeah, great question. I mean, I think there's a few considerations there in packaging. Our choice, we have a history of chiplet architectures at AMD. We've been doing this for a while in our EPYC processor lines and even in our Ryzen processors for PCs. The ability to use mixed technologies is one advantage for using chiplet architecture like we have in MI300X. We're able to select the process silicon technology that's most appropriate for the type of IP that we have in each of those chips. Additionally, by using 3D architecture, we're allowed, silicon on, I'll just say 3D architecture without being more specific. It allows us to have a smaller package footprint, right? And part of the considerations is not just the 3D packaging, but how do you build a reasonably sized finished product that doesn't require a interposer module size that pushes you into technologies, beyond what are reasonable for manufacturing. So our experience in advanced packaging led us to this solution, and it's proven to be a very good solution because we were able to ramp MI300X into volume production. I will say that we did have previous experience in 3D packaging with our EPIC product line as well. We do have the Vcache that we sell on some of our EPIC processors, so we already had significant volume manufacturing data on 3D stacking that it gave us the confidence to bring that into volume manufacturing on MI300.
Take another one from the audience here.
Yeah, Nathan Brookwood, Insight 64. In that 8-chip configuration, how do you handle cache coherency across all those chips? Or do you?
We do. Yeah, we do. So I mentioned in the talk that we have hardware-assisted and software directives that allow us to maintain coherency between the accelerator chiplets that are connected to the 4 iodize. It's a little bit complicated. In fact, we had considered putting it in the talk, but we pulled it because it was so complex. So what I would do is we'll put some information in the Slack channel that describes the coherency. So we'll put those links in there.
Yeah.
Are the accesses then broadcast to all the different nodes and you have to wait for responses, or is there some sort of
Yeah, I can say that we do have probe filtering, within our architecture. So we only send, directed probes.
Thank you.
We have about half a minute left, so I'm going to take the last one from the audience, and the Slack ones can be answered offline.
Hi, Charlie Demergent from Semi-Accurate. You've shown 4 GPU plus 0 CPU, 3 plus 1. Can the architecture support arbitrarily mix and match between 4 plus 0 and 0 plus 4?
You're talking about the APU? The CCDs and XCDs, you mean? Yeah. Yeah, so I guess I can't really talk about product configurations that, other than what we've shown. The architecture's flexible.
Thanks.
Thanks, Alan and Vamsi.
Thank you.
Well, our next talk in this section, is from Broadcom, an AI compute ASIC with optical attached to enable next generation scale-up architectures. And our speaker will be Manish Mehta. Manish leads the marketing and operations teams at Broadcom's Optical Systems division, which is now developing highly integrated silicon photonics for co-packaged optics solutions. He's worked on programs for over 10 years to develop and ship conventional optical interconnects into the cloud and AI clusters, forming his point of view on what is required for the next 10 years as AI cluster architectures evolve. Manish?
So thank you very much for the introduction. My talk will be quite different than the others that have preceded. I'll be talking about optics, but very specifically the progress that we've been making trying to facilitate optical attach directly to GPUs. And in Broadcom, our co-packaged optics journey has really been to develop very high-density integrated silicon photonics that will reduce the cost, the power consumption, the latency, and improve the reliability of the optical interconnect, much of which is deployed in the scale-out networking today for AI networks. And in addition to that, we've really been focused more recently on trying to ensure that we can build these interconnects at a shoreline bandwidth density and build a platform that will meet shoreline bandwidth densities that are important over the next few generations of both scale out and scale up architecture. I'll walk you through some of the first products that we have developed using co-packaged optics, which are more on the networking space with Ethernet switching. And we have now developed some test vehicles where we've actually taken these optical engines and done more complex packaging with GPU-type devices. And we'll be talking through the implication over the next few generations of the CPO platform on next generation scale up and scale out. So I'll start just with quick summary of the problem statement. Most of the scale out for sure, and even the scale up, is serialized PAM4 links today. If you look at InfiniBand or Ethernet or NVLink, most of what's shipping today is going to be 100 gig PAM4. We're on the cusp of proceeding to 200 gig PAM4. And with every one of those generations, we know that the loss is increasing, and it's becoming very difficult to extend the reach of the copper cables beyond potentially rack to rack. There's been great engineering on the SerDes to get rack to rack connectivity, but that is about the limit. So any type of cluster development that's going beyond that kind of 3 to 5 meter range is going to require some type of optical reach, and that really has mandated the development of optical interconnects that are co-packaged with the ASIC. So, in scale-out networking today, most of those pluggable modules that are deploying look like what you see here in this image. It's a very discrete type of module. These are 400 gigabit or 800 gigabit pluggable modules. They have a large number of discrete components like lasers, photodiodes, lenses, and filters, and they're assembled in a semi-automatic fashion at many CMs and module manufacturers globally. And there's about 15 million of these that are shipping into scale-out networks in 2024. If you think about the type of bandwidth that could be required if there is a need for scale-up to progress to higher reach and therefore optical connectivity, you're going to need 10x of that bandwidth, and that just will not be achievable with this type of paradigm. So the industry has made a lot of progress over the last 5 to 7 years, starting to do the first level of integration and taking some of that optical functionality and placing it into a silicon photonics chiplet. These are fairly low scale levels of integration. You're doing maybe 4 or 8 channels of functionality onto a given silicon photonics PIC, photonic integrated circuit, but it is a very important step to where we need to go for true co-packaged optics. And these have started to ship in production, but they're still, again, limited to about 4 or 8 channels, maybe about 10 to 30 devices, optical devices on one of those photonic integrated circuits. So what we initially did was build higher density silicon photonic based optical engines that are co-packaged with Ethernet switching. And this is a device, it's called Bailey, that I'll speak more about shortly. But this device has a 51T Ethernet switch surrounded by 8 optical engines. Each one of these optical engines is 64 lanes of 100 gig. There's about 1,000 optical devices on that photonic integrated circuit. Now, that's certainly not at the level of the 200 billion that we heard earlier in terms of transistors on Blackwell. However, in the scope of optical integration and moving to production, this is one of the first step functions we're seeing in integration taking place for optics. And then what we've done is we've taken one of those optical engines that, again, operates at 6.4 terabit per second, that's duplex, so both TX and RX, and we've packaged it with a more complex CoWoS device. And I'll speak through what we've seen in that execution, but this really is, we think, one of the first steps towards facilitating that optical attach directly onto a GPU. So, just a quick background on what this platform looks like, because your chassis or appliance is going to look very different than what you're going to see on a standard device. So on the left, you see your CPO device. It has some core logic. It could be a switch. It could be a GPU, surrounded by your optical engines. This and all of the high speed, all of your, say, 100 gig PAM4 or 200 gig PAM4 is now contained electrically to that package. None of that signal is now traversing into your PCB. Instead, you're doing the optical conversion directly on that package. So you take that signal to the front panel using optical, fiber cables within that appliance. One thing that we did do at the request of customers and just understanding where the failure modes are on optics, we have taken that continuous wave laser, that's the compound semiconductor element that generates the light, effectively your light bulb, and we've disaggregated it into a pluggable module that is field serviceable. So everything that's on that integrated package next to the switch is silicon. It's either silicon photonics, or it could be silicon germanium, or CMOS. And there was about 4, I would say, very important components that we developed in order to build these optical engines. We had to build the photonic integrated circuit, which has your Mach-Zehnder modulators. It has your photodiodes. We have an electrical integrated circuit that has your Mach-Zehnder modulator drivers. It has your TIA circuitry. And it's the attach of those 2 chips through advanced packaging. I'll show you a few types of that momentarily, that generates your optical engine. And then in order to, the amount of signal you're now extracting optically from these devices is much higher than you have in a standard optical format. So we've had to develop high density fiber connectors that are also detachable, so that you're not taking this, a glued fiber on an optical engine and having that on a package that you're taking through reflow. So we developed a detachable optical fiber that you can remove during the manufacturing process and very easily assemble in the final construction of the box. So our first generation device, it was a POC, it was a proof of concept device. It was called Humboldt, and it was based on Broadcom's Tomahawk 4 Ethernet switch family. It's a 25T Ethernet switch where we had half of the bandwidth, 12.8T, that we were still doing conventional electrical extraction. So it was running through the PCB to the front panel, to front panel ports that, again, for DACs or pluggable transceivers. And the other 12.8T, we had 4 3.2 terabit optical engines. Each one of these optical engines was 32 channels of 100 gig per lane, and it was a silicon photonics PIC bonded to a silicon germanium EIC. And each of these optical engines had about 250 optical components. It was a very important learning process for us, I think for the industry as well, but there was a key weakness, which is that silicon germanium dissipates an additional 3 picojoules per bit of power compared to what you could achieve with CMOS. So in order to construct this, we have a silicon photonics PIC, a silicon germanium EIC, as I mentioned, but one of your chips, in this case it's our EIC, has to have high-speed connectivity both to your substrate, which is communicating with your core logic ASIC, and to your PIC. So you need a double side attach for that EIC, for which we used a TSV process through our EIC. And you can see, some of the cross sections here. The top shows kind of an extraction, a more zoomed out PIC to EIC bond. Next to, it's on a common substrate with a logic ASIC. In this case, it was a signal processor. And then you can see zoomed in what some of the cross-sectional bumps for that PIC to EIC attach look like on the substrate. So then for our second generation system, we made some modifications. It's called Bailey. It's based on the Tomahawk 5 chip at Broadcom. It's a 51T Ethernet switch. And here we transition to all optical connectivity. So all 51 terabit is extracted from the package optically. It's using 8 6.4T optical engines. And here now we have the PIC bonded to a CMOS EIC. It's a 7 nanometer CMOS EIC. And each of these optical engines now has 1,000 optical components. We've gone from 32 lanes to 64 lanes. That's one of the reasons for the increase. But we also, with CMOS, were able to apply a lot more control circuitry and logic into our EIC itself. And therefore, we had some optical components that we could embed into our PIC that could take advantage of that additional control. And the picture you see on the left side kind of gives you a visual of what this looks like inside of a chassis. You have at the center of that package, you have your CPO device, the switch and your optical engines, and then you have optical fibers that are connected to those optical engines and then connect to the front panel in order to get the signal out of that chassis. So here we migrated from a TSV process to a fan-out wafer-level packaging process, FOWLP. And it's a process that's been used broadly in the mobile handset market, and it's very widely deployed within the OSAT community. So that was one of the key reasons we selected it. We knew we really needed to scale this generation, so we selected that process. And that FOWLP has improved the scalability and the stability of that PIC to EIC bond. So some of the details of how exactly we build this, we have to take our EIC, and again, we had to implement double-side attach to this reconstituted EIC die. Again, PIC on one side, substrate on the other. So we have a thin EIC that we then singulate and we encapsulate in a mold to build a reconstituted wafer. That mold also has your RDL layers, and then you do a silicon photonics PIC chip attach to that reconstituted wafer. So that's your chip to wafer attach. Again, done at wafer scale, using OSAT processes. And then we singulate each of those engines once the PIC is attached to the EIC. And we attach a few components to get the light in and out of that device. And then we have to take, in this device case, 8 of those optical engines and bond them to a common substrate with your core logic ASIC. And you can see here, and on the left side, it just shows a little image of your core ASIC surrounded by your 8 optical engines. And then you can see again, the cross sections where these are taken after all 8 engines have been attached to the substrate. And that PIC to EIC bond is very stable. But more importantly, that TMV, that's your through mold via, the attached to your copper pillar, attached to your substrate, was also far more stable than we observed with the TSV processes. And we've thus far seen very stable performance during reliability testing as well. So the conclusion of that kind of spatially, if you look at it just sort of in terms of space, is we've taken what deploys today in a scale-out network, right? 51 terabit of optical connectivity. That's either done today using 128 400 gig optical modules, or 128 400 gig optical modules, or 64 800 gig optical modules, and we've collapsed that into 8 optical engines, which are basically 17 millimeters by about 15 millimeters. And the visual you see on the right side, that picture kind of shows what all of those modules would look like on a table, and the collapse into the device that's in the center. But you get other benefits through that integration. You're eliminating complexity in your signal path. You can actually get rid of circuitry. You can get rid of a lot of the DSP processing that's required when your optical interconnect is so far away from the core package that you start to see improvements elsewhere. So for example, a conventional 800 gig optical module will consume somewhere between 13 and 15 watts of power. So that's for one module. At a system level for a 51T switch, this is about 1 kilowatt of power consumption on optical modules for that switch. So what we've been able to demonstrate is we can reduce that to about 5 watts, that 13 to 15 watts to about 5 watts. And that's simply because of all of the complexity you've removed in that signal path. More recently, we have been able to optimize our performance. There was a lot of work getting to what we feel is qualifiable performance, but very recently, TDAQ is a measure of the optical eye quality, and this is probably one of our better eyes, but we've been able to achieve TDAQs that are very close to 1. If you look at our distributions over a system that has all 512 lanes operational, you'll probably see a distribution that's about 1 to 2 for that parameter. But more importantly, what we've seen is that we're getting very tuned in to how to look at post-FEC error statistics for optical module links based on optics, and really starting to look at FEC tail distributions and the decay of the FEC tail curves to understand the quality of our devices and our integration. So this you can see on the left side, and don't need to focus too hard on each of the items, each of the boxes, but this is 72 of the 128 400 gig ports that I've extracted. And what we're looking for is a very steep slope on that, on each of those curves, and definitely no roll-off that could signal that you may start to see uncorrectable errors and link flaps in operation. So we ran these with a few hours of gating time. I think it was about 2 hours of gating time, and we saw that all of our ports were operating with 6 or less FEC tails, based on a production chassis. So this is built in an ODM environment in a production on a production grade chassis. But we do want to see some further improvement on that. So more recently at a lab level, we've seen how we can reduce that FEC tail extinction to about 3 symbol errors or less. And this is an example of one optimization that we've done in lab, where we've taken one optical engine, that's 16 400 gig ports, and on 14 of the 16 ports, we're able to achieve pretty compelling statistics. There's 2 ports that we're still working on optimizing and seeing if we can even get to that 3 level across an entire optical engine. And then in terms of power for the whole chassis, what we've observed is that if you were to populate this system with all pluggable transceivers, each of these transceivers would have DSPs. You'd have about 2 kilowatts of power consumption for the whole system, and we're able to reduce that into about the 1.35 kilowatt range. What this means is, like, if you build a 32K GPU cluster, you have kind of a non-blocking network for the scale-out compute. It's about a megawatt of power consumption savings that you can achieve with this level of power consumption reduction. So then that's the device that we're planning to first take to production. But it was very important for us to take that device and understand what the implication would be if you try to package those optical engines with more complex devices that are more similar to GPUs. So we worked very closely with the custom ASIC team at Broadcom, the APD division, and they built a kind of a test chip that emulates a GPU. So it's a core kind of logic die, 2 HBM stacks, and a SerDes tile. So it's a CoWoS device to which we went through a packaging process of a single optical engine, one 6.4 terabit optical engine onto this package. And we were able to demonstrate error-free performance. There is more complexity here. On the previous devices that I showed, both the core logic, the Tomahawk 4, the Tomahawk 5, and your optical engines are both bonded directly to the substrate. Here you now have that additional interface. You have the signal propagation through the interposer, through which you do have to overcome the signal integrity impairments. And thus far, seeing that we can achieve error-free performance and now need to work on optimization to hit the right post-FEC levels. But mechanically, thermally, we were able to achieve attach of those optical engines to the substrate without inducing any warpage concerns. And the reason we think this is important is because we want to facilitate, enable the ability to do optical for scale up. Whether that has an application or not is certainly not our expertise. But if you are able to move the scale-up domain to optical, you can start taking advantage of first-layer switches that could have 512 logical ports and build clusters without having to worry about reach, because you get that from the optics. Build 512 GPU clusters in the scale-up domain, and using upcoming switches that should be available. And if we think about how do we progress beyond that, 6.4T is a decent number that's today for scale-up bandwidth requirements today. But we do, from all of the work we've been doing and the progress that we expect to make towards 200 gigabit per lane optics, we do expect to have a pathway to achieving 8x that bandwidth capability. So just to give you a sense of how we build that, as we mentioned, right now, we've kind of started to prove that we can attach 6.4 terabit optical engines, 64 by 100, to a GPU type device. That's duplex, so if you look at it TX plus RX, it's going to be 12.8T. By 2027, we expect to have in production 12.8 terabit devices. And across a substrate, because we're bonding our optical engines to the substrate, not placing them on the interposer, we're able to do some level of fan out. So you have all, let's say, for a CoWoS S-type device, all 80 millimeters of an edge of the substrate available to do the bonding of your optical engines. So you can easily achieve 2 optical engines, which would be 25.6T duplex. And then as you move to CoWoS L and you move to substrates that are exceeding 100 millimeters on an edge, you will be able to achieve attach of 4 optical engines or 51.2T duplex or 102.4 TX plus RX to a given substrate edge. If you're able to use both the north and the south, assuming your east and west are used for HBM, if you're able to use both the north and the south edges, then you can double that for your available I/O that you could extract optically. And then finally, as you start to look at these high radix networks and you think about deploying them optically, whether it's for scale up or for scale out, in your network cost calculations, fiber does start to become relevant. And so one of the things that we have looked at and published a white paper on recently was how you can move to very high radix connectivity, not compromise on radix, but cut your fiber count, your I/O fiber count in half. So one of the nice things about optics is you can actually send your TX and RX on the same channel. Channel in this case happens to be the fiber strand, by using wavelength division multiplexing. So by having, what we've done is presented a solution where you would have your TX and your RX on different wavelengths. You can then transmit them down a single fiber, both TX and RX. You can maintain your maximum radix, and you can cut your fiber count in half. And this was just a simulation we did on network cost for 2 types of scale-out architectures. One was a 32K GPU cluster, the other was a 64K GPU cluster. We looked at various types of optical modes, whether you have 8 wavelength, 4 wavelength, bi-die or single wavelength. And in every single one of these, at least in both of these, and if you take it larger, it's even more pronounced, you can minimize your network costs by moving to a bidirectional type device, which you can sort of get in a very cost-effective way through high-density integration in silicon photonics. So rather, I don't have a conclusion slide, but I do have a video on how we sort of are building these devices. And this is the device you've seen. This is Bailey. It's the 51T switch. And we start with optical wafer sort. This is our PIC device where we do optical testing. We then do the FOWLP. This is a video for our chip to wafer attach that again is done at wafer scale at OSATs. After that, I mentioned we have to get the light in and out of these optical engines. So we have to attach lenses, we have to attach fiber holders. So we've worked on automating the process and the tools that can allow us to build these optical engines at scale, minimizing variation, trying to optimize reliability. We can test the full transceiver capability at the optical engine level, and then we can proceed to attaching these optical engines to the final device. So you have a known good optical engine going onto your final device, and then you can do some, we're not there yet, but you should be able to do some fairly simple testing at your final device level in order to complete your known good device using co-packaged optics. So thank you, and open to questions.
Thank you, Manish. Okay, do we have a Slack question?
We do. Actually, we kind of have two that I'm going to combine.
All right.
So the first part of it is, can the same SerDes be used for scale-out optics and for the same protocols running on electrons within the rack? And then Alyssa kind of asked the same question. What is the protocols that you're running?
Yeah, you can certainly use the same SerDes architectures for whether it's for scale-out or for scale-up. There may be some optimizations we can do as we get better at this in terms of not needing as much power for some of the scale-up requirements, which will be shorter reach than you would need for scale-out. But initially, I think we're trying to drive some commonalities so that we can get some good data and volume on common protocols.
And is the protocol that you're running something like LR?
Yeah, we're starting with LR-based Ethernet SerDes. Again, that probably is overkill, but right now, when you're looking for margin in order to just get this off the ground and get the industry comfortable with the platform, we're going to maintain that for some period of time.
Thank you.
Nathan?
Yeah, Nathan Brookwood, Insight 64. How do you generate the light that goes into the chip to go out on your PHY?
Yeah, so what we've done is we have indium phosphide continuous wave lasers. They sit in a pluggable module that plugs into the front of your chassis. So one of these modules has 8 of these lasers. Each laser pumps anywhere from 400 to 800 gigabit of bandwidth, depending on how much split ratio you need. So that same fiber cable I showed that has your I/O signal go to the front panel. It also, that same cable has strands that bring your CW light into your optical engine.
Great, thank you.
Slack question?
Indeed. We have some that several people have jumped on. Right. Silicon photonics, as I understand it, requires narrow, stable temperature range to achieve good signal and reliability. How do the co-packaged optics handle heat? Or is my understanding incorrect?
So it's true that the active optical component is very sensitive to temperature. What we've done is, in this architecture, we've extracted that, right? So we've moved it to the pluggable source at the front panel, where in our design, you don't even need to cool that device because your power generation on the overall chassis is so low, you can maintain an uncooled temperature for that device that allows the CW laser to remain operational. And then if you noticed, I mentioned we have a detachable optical connector and it's edge coupled. What that allows us to do for the embedded device is have a common heat sink for both your core ASIC and your optical engines. You can use that same kind of footprint, that size, in order to do the heat extraction. You do have to manage through the thermals, but the sensitivity isn't necessarily there. You just have to ensure that you're not hitting junction temperature limits. So.
Okay. Audience question over here.
Hi, Chris Weiland, Samsung. Question, okay, Trevor brought it up earlier today about, reliability.
Yep.
Optoelectronics reliability.
Yes.
So the question is why do you have the transceiver on the package rather than as a miniaturized QSFP or something like that?
Yeah, because any way you skin it, no matter what is possible today, if you want to minimize circuitry complexity, if you want to get rid of having to attach a fully functional DSP to the optical engine, it has to be on package. And that device is that additional 60%, or no, that additional 3x power consumption that you would generate. So rather what we've done is take an approach by saying, okay, we accept that the active optical device is a point of failure. We don't think that's going to be the case based on some of the material choices you have, but we're going to extract that anyway, make it field serviceable, and now the optical engines that are embedded and on package are truly like silicon devices that are manufactured in OSAT environments. And we're working through the next year, proving out that reliability, but the current data shows that that's not going to be the point of failure. What we really need to focus on is the actual assembly of these chassis and the workmanship of like the fiber connectivity into the optical engine and into the front panel, because if that also were to break, that is a source of rework that would be challenging. So.
Great, thank you.
Audience question here.
Huichao Xu from Teradyne. In the work you presented, what is the actual power efficiency numbers on the system level end-to-end picojoule per bit? Do you have the number?
Yeah, so I believe that the optical interconnect element itself is right now about 6.5 picojoule per bit on one end. Okay, so double that if you want to go end to end. And then the LR SerDes is somewhere between 3.5 and 4. So if you add that to it, so you've got 10 one end, 10 on the other end. So that's your link is about 20 picojoule per bit. So.
Basically 20 picojoule per bit for both PIC and AIC.
PIC, EIC, and the compensation circuitry that you have on your SerDes in order to, the DSP compensation that exists on the LR SerDes to do the, the signal compensation for the optical engine.
Got it. Thank you very much.
Okay, we're over time now, so we'll have to call an end to it right now. Let's thank Manish.
Thank you.
And our last talk in this session is entitled RNGD, Tensor Contraction Processor for Sustainable AI Computing from Furiosa. Our speaker is Jun Pak, who's the founder and CEO of FuriosaAI. Before he founded FuriosaAI in 2017, he worked as both a hardware and software engineer at AMD and Samsung. Jun holds a master's degree in electrical engineering from Georgia Tech. Let's welcome Jun.
Hello, everyone. I'm Jun. It's a pleasure to be here at Hot Chips, and I'm very excited to share with you our second generation chip, Renegade, for the very first time. So today, I'll walk you through Renegade from several key angles. First, I'll introduce Renegade as a product, why this chip is built, how this chip came about, and what makes it a unique product. Then we'll dive into its hardware architecture and the chip design, including our approach and the foundational innovations driving our work. Lastly, the software part, where the vertical integration of software is just as critical as the hardware. So in order to introduce Renegade, I'll describe what led to the development. We started about 7 years ago in 2017, when AI models were already showing transformative impact on the world. We believed AI will be everywhere in our daily life, and the inference will become social infrastructure like water and electricity. So from the very beginning, our goal was to build efficient and high-performance inference chips designed to serve AI at scale in data centers and infrastructure. While training is about building AI models, inference is all about AI services and deployment. So for inference, the response time for end users matters, and sustainable cost and efficiency are critical for businesses. Our initial design in 2021 was optimized for bird scale models. However, we soon made a major shift in our design when we witnessed the emergence of foundation models such as GPT-3, a model 5 times larger than BERT. Even though those gigantic models were primarily in research phase, we betted on its future potential. Despite risks for a startup in building a large SoC to accommodate those big models, we believe that people would gravitate toward the most capable AI models because more intelligent models offer greater benefits. We also believed efficiency was bound to become even more critical as we scale the development of these LLM-based applications. So we set out to make Renegade the most efficient inference-dedicated chip for serving the most advanced AI models both now and in the future. So here comes Renegade. I'm showing the chip here. So it delivers robust compute performance of a 512 teraflops of FP8 and 1 petaops of integer 4, along with the full support for VF16 and integer A. One of its standout feature is its exceptional memory performance, driven by 2 HBM3 stacks that provides up to 1.5 terabyte of second of bandwidth, along with a 256 megabyte of on-chip SRAM, up to 384 terabyte of second of bandwidth. We intentionally designed a higher compute-to-memory ratio as memory bandwidth more dictates overall performance in large language models. We aim to strike the right balance between compute and memory performance. And let's talk about power. While delivering high performance, Renegade has a target TDP of 150 watts. This power envelope is well suited for existing air cooling-based data centers, which are optimized for handling this power range. This means you can seamlessly update your current data centers and server into powerful AI engine without the need for costly infrastructure overhauls. So to achieve our ambitious product goals, the Renegade chip is built using TSMC's advanced 5-nanometer node, packing 40 billion transistors onto a large SoC die. We've utilized 2.5D packaging, which integrates the HBM modules and SoC on a single silicon interposer. Additionally, we are using the latest 12-layer HBM3 memory to ensure top-tier performance, capacity, and efficiency. So let's take a look at our early number. The key metric here is performance per watt, measuring the efficiency. To accurately assess this, we use the MLPerf benchmark, which is well suited for this purpose. The MLPerf load generator simulates a variety of context input lengths based on a real-world distribution, making it an ideal tool for measuring performance in a way that mirrors actual use cases. While GPT-J is not the most recent model, it represents a standard language model architecture. This means that the performance optimization we've applied to GPT-J can be broadly applicable to other LLM models as well, such as the Llama 3.1. So we've achieved approximately 11.5 query per second, which means like we are processing almost a couple of thousand tokens per second as input, and the output is almost like 1,000 tokens. Here, like we are talking about queries of like a couple hundred lengths, with a measured board power of 185 watts. This gives us almost 60% higher performance per watt compared to L40S. And it's also worth noting that it took us only 3 months since the arrival of our silicon to reach this level of performance and power, and we have a substantial room for further improvements in the coming months. So we are now running Llama 3.1 70B models, and actually over this weekend, we have the updated performance number of 12 query per second. So we'd like to elaborate more on the inference efficiency, especially in the context of LLMs. AI inference efficiency is not just about hardware. It comes from hardware efficiency, software efficiency, and algorithm efficiency. This includes a wide range of techniques from model architecture, software optimization, to quantization. With the ongoing improvements every day at every layer, the silicon architecture must be quickly integrate these efficiency innovations. In other words, the AI chip architecture needs to be not only efficient on its own, but also highly adaptable and programmable to keep pace with these evolving optimizations. If you log in on a specific set of optimization without flexibility in the hardware, the chip's overall efficiency will ultimately fall behind the competition. So what is our approach to hardware architecture and chip design that can achieve both efficiency and this flexibility, programmability? One of the biggest challenges in our view for building AI chip is getting the abstraction right. So over the last 7 years, one of our core efforts has been refining this abstraction layer. So we'd like to talk about this one. So one key observation in deep neural network computation is that tensor contraction dominate deep learning operations. You see that in transformers, which are the basic structure of most deep learning models today, key operators like feed-forward networks, linear layers, and memory in attention mechanisms are all tensor contractions. An analysis of BERT shown on the right shows that 99% of its flops come from these operations. Tensor contraction are a core fundamental computation in deep learning. You can think of them as a multi-dimensional form of matrix multiplication. In fact, matrix multiplication is just one specific case of tensor contraction. However, most commercial deep learning accelerators rely on fixed-size memory instructions as their primitive. So we are proposing a domain-specific architecture for deep learning, which we call a tensor contraction processor. Instead of using memory instruction as primitive, we want to raise hardware-software interface to accelerate whole tensor contraction as a primitive. By doing this, we can streamline hardware, leading to higher performance and better energy efficiency, while providing enough flexibility to support all deep learning models. So tensor contraction is declarative. It's a mathematical expression without explicit scheduling for computation or explicit memory layout for data. The equation on the right is a tensor contraction expressed using Einstein notations. If you look at this example, it doesn't show any computation order, parallelism, or how the data is laid out in memory. So the tensor contraction is expressed in INSUM into a primitive that can be executed by the real architecture. We introduce a low-level INSUM notation. This low-level INSUM notation combines tensor contraction with explicit memory layout and the scheduling information. I'll explain how this low-level INSUM allows tensor contraction to be executed efficiently as a primitive in our architecture. So this is the simplest example of tensor contraction. So tensor contraction is a more multi-dimensional thing, but to make this explanation simpler, we just choose this two-dimensional memory. The image on the left shows a case matrix A and B are multiplied to produce a matrix C. This computation can be described using a for loop. From the perspective of the actual chip architecture, this computation is executed in parallel by multiple compute units and SRAM. To keep the explanation simple, let's consider a chip composed of 4 SRAM blocks and 4 compute units. We can take the conceptual computation from previous slide and express it as a scheduling on the actual architecture. So outermost loop in this example represents the axis that's executed in parallel. The innermost loops represent the unique computation executed every cycle. The remaining loops represent scheduling that utilize these distributed compute units over time. Specifically, when you look at loops that make up temporal scheduling, axes have some additional meanings. For example, the axis marked in blue indicates that data stored in one SRAM are used by multiple compute units, meaning it can be multicast. The axis marked in red indicates that input data for a unit computation can be reused for consecutive cycles. So I'll explain the architecture for accelerating tensor contraction along time and space axis and its advantages. First, looking at the architecture on the left, we see that to handle data sequentially read from SRAM in a pipeline manner along the time axis, the compute unit is organized into fetch, operation, commit stages. We define a slice as a unit that combines one SRAM into one compute unit. In each slice, the fetch unit fetches a tensor in the order given by the temporal scheduling. Fetch data then can be multicast to multiple operation units via the fetch network. Fetch network can be configured in various topology depending on the given tactics. Data supplied through the fetch network is delivered in the defined order to the contraction engine. Contraction engine uses the feed buffer to reuse this input data multiple times. As a result, data read once from SRAM can be multicast and fed multiple times. Additionally, with the temporal pipelining, we can continuously utilize spatially distributed connected compute units during tensor operations. All data paths, including fetch unit, fetch network, feed buffer, can be streamlined. This hardware operates simply according to tactics defined by software. Software finds optimal tactics for given operations. But this software is actually a compiler. Also, using sliced SRAM and compute unit is more advantageous for inference than having a large matrix multiplication unit, because we can flexibly configure them according to the tactics. Large matrix multiplication units can achieve a high utilization with a large batch size. However, during inference, batch sizes can vary widely, leading to kind of low utilizations. Therefore, it's important to exploit the inherent parallelism and data reuse from various axes in tensor operations. In the slide, we see two configurations using 4 slices. In the middle configuration, the same data is reused 4 times through the fetch network. This configuration is quite similar to large systolic array, transferring the same data along the height axis. Alternatively, as shown on the right, every 2 dot product engine can be configured to calculate a single dot product along the width axis. So by configuring multiple slices to fit each tensor operation and pipeline them along the time axis, we can better exploit parallelism and data reuse for a variety of tensor shapes. So Renegade actually is the implementation of a tensor contraction processor. This Renegade features 8 processing elements with 64 teraops and 32 megabyte SRAM with 64 slices. Each PE processing element is actually independent AI core. It can function independently or be fused with up to 4 PEs to act as a single large processing element. So for more detailed architecture, microarchitecture, you can refer to our ISCA paper we presented this summer. So explaining our backbone interconnection network, we use multiple hierarchies of on-chip network to manage connectivity. Inside each processing element, network NOC within PE connects various components, including the internal CPU, scratchpad memory, and the tensor cores. For external connection, the network router handles communication between each PE and HBM, or between processing elements themselves. The NOC for HBM memory also facilitates the full channel interleaving, efficiently utilizing all 16 HBM channels and enabling each PE to access the HBM at its full bandwidth. We use PCI Gen 5 with 16 lanes for the both host interface and chip-to-chip communication. For chip-to-chip communication, we use the PCI switch for direct communication between chips to reduce the latency and enhance performance. The PCI fabric networks allows us to scale up to 20 Renegade chips in a single server, supporting large models like Llama 405B by partitioning them into multiple chips. So we now run like Llama 70B with the 2 chips or 4 chips. So Renegade also leverages the SR IOV feature to support up to 8 multiple instances. Each PE or fused multiple PE can function independently as an AI core, so you can allocate 1 to 4 PEs to each virtual instance. This allows Renegade to provide multi-tenancy in cloud server, enabling high utilization by multiple users. We'd like to briefly touch upon the engineering challenge of HBM integration. So while HBM provides impressive bandwidth, it requires an interposer to handle the dense routing. Since the interposer itself is difficult to test separately, careful design and verification are crucial for successful HBM integration. We conducted a full wave 3D electromagnetic simulations to model interposer accurately to ensure we have a right signal security and the power security. So now we'd like to talk about the software. We invest much resource to a full stack software for Renegade, and all these components are vertically integrated and optimized. So this is an overview of a Furiosa LLM software stack for high-performance serving for LLM models. This entire stack will actually utilize for our performance numbers, benchmark performance as well. Currently, we are focusing on PyTorch 2.0 support, and our flow starts from PyTorch model. So by leveraging PyTorch's Torch Dynamo and FX graph, we convert the PyTorch model to a computational model graph. Once Furiosa LLM gets the model graph, it quantizes the model into a low precision model first. Then the next step is to apply various parallelism strategies, such as a pipeline or tensor level parallelism, targeting multiple PE to multiple chips. Then we come to have numerous smaller partitions of those models. Then it's fed to the Furiosa compiler. So Furiosa compiler compiles each partition, and the runtime loads compile the binary with partition weights to multiple devices. So if you are going back to the compiler, so the compiler takes the partition model graph as an input, optimize it for end-to-end model efficiency automatically, and generates an executable. So for any given operator's load shape, there is a tactic space composed of a permutation of axes. The compiler selects the optimal tactic from this tactic space based on performance and power estimator. So you need quite accurate performance and power estimator to have the right compiler. So optimizing an end-to-end model involves selecting the optimal load shape for all operators to minimize cost. So compiling a model involves many optimizations across multiple levels of IRs. This optimization process includes operator fusion at the graph level, memory allocation, tensor splitting, merging, and the scheduling. And the mapping tensor onto on-chip memory significantly impact the performance and energy efficiency. So how we lay out this memory is a very important part of this performance. Firstly, the last axis of memory layout impacts memory access performance. For example, whether the stored layout is row major or column major, or its alignment with the leading patterns affect the SRAM bandwidth. So we like to utilize the full SRAM bandwidth. Secondly, since the data is often used across multiple compute units, Memory layout impacts all the data movement, thus the performance energy of the network on chip. Thirdly, output tensor of an operator is often the input tensor for the next. Ideally, compiler can align the memory layouts of input-output tensors of operator. If we can do it, it can completely eliminate unnecessary data movement. So it's finally we'd like to talk about our serving framework. So Furiosa runtime serving framework is a software component for end-to-end high-performance serving. Here, continuous batching and page attention are the state-of-the-art optimization techniques. Both techniques allow large batchings and allows to reduce significantly the latencies in production. So our serving framework and LLM adopted many state-of-the-art optimization, including both. For example, it provides VLLM compatible API. VLLM is basically based on CUDA. Attention kernel implemented CUDA is one of the key parts of VLLM. Instead, we just use the PyTorch A10 ops to implement paged attention logically. And the Furiosa compiler compiles the implementation of this program fully optimized for Renegade. I think this is a much more scalable approach to implement the optimization. It's why we can do this in a very quick, short amount of time, leveraging all this automatic compiler and the high-level language. And the quantizer, the benefits of quantizers are well known, and often its complexity lead to hesitation in its adoption, but we are committed to minimize these hurdles. So we fully automate the entire quantization process, and we support a wide range of quantization schemes. So from the most conservative BF16 to more aggressive state-of-the-art schemes like AWQ and the GPTQ. So we are a startup company with like 100 people engineering team. So we try to have the most advanced development methodology. So we try to use one of the best language for developing our chip and software. So our software is entirely written in Rust language. And we also use extensively Chisel language, Scala-based Chisel language for our RTL development. I think this is one of the largest Chisel-based production chip. And it significantly helped us like automate all this development. And we also use the Python as well. So yeah, this is the end of it. And thank you for listening. Okay.
Thank you, June. Yeah. Okay, we're ready for some questions. I know there were a lot of questions in the the snacks are coming. The Slack channel, and some of them had already been answered. Are there any that June should still answer?
Yes, I think there is one that just slipped off the screen. So Kieran G asked, is the abstraction simply dot product with flexible lengths?
Yeah, I think, as I probably explained, like the memmer is a very special form of tensor contraction. So it's very different. I mean, this using memmer as a primitive or using this tensor multi-dimensional matrix multiplication as a primitive is kind of different thing. Definitely, you can describe this tensor contraction all in a memmer way. But it makes these things very complicated things, actually. So it's why abstraction matters, I mean, in our opinion. Yeah.
Okay, question from the audience.
Yeah, I'm Daniel. I'm Daniel from Anafleshi. Yeah, thank you for your presentation today. Well, actually, yeah, it seems that there are 8 PEs and 8 slices in each processing element. So, what is the reason to decide the number of the processing element and slice for each PE?
Okay. So actually, the slices work quite synchronous way. So the PE is, can be considered as a kind of a programmable core for us. So we try to have the right balance. So we like to have a kind of large core, but we like to have some flexibility inside the large core compared to like a large solid array. So that makes like we have like a relatively smaller number of PE, programmable PE. So we just have 8. But inside this PE, we like those kind of flexibility and make us choose this 64 as the ideal like number. But you can have like actually 48 as well, I think. But yeah, I need to ask our architecture team. I checked the region, the number region. Okay. Yeah.
Another question from the audience on the other side here.
Yes, if Tanj Bennett from Semi-Analysis. If I understand, this is a form, the memory ordering is like a form of stride management. And you mentioned managing the ordering in the SRAM to optimize reuse. I didn't catch whether or not you organized the fetch, excuse me, from the HBM to minimize the number of activations, perhaps doing prefetch along a row activation in anticipation of being able to reuse some of that data for the stride.
Yes.
Do you do any of that?
Yeah, that's one of the major optimization we have. Once we patch data from HBM, we like to use it as many times as we like to use, so that we just minimize this energy expensive like movement costs between HBM and SRAM.
Okay, I have a related follow-up then. There is some talk of there being optimized base chips in the HBM or customized base chips in HBM4, which already have at least 2 clearly announced forms, but some talk of optimization. Do you think that sort of stride management would be an appropriate thing to move into a base chip for the HBM stack?
Yeah, I think there could be some area we can benefit using the base die between HBM and the chip. I don't know specifically where we can get the benefit, but like I think yeah, there should be definitely some, not the entire thing, but some area we can have a good benefit out of those base die.
Yes, well, they're talking of having FinFET chips, so there'll be significant amounts of potential logic on those chips, subject to probably thermal constraints.
Right.
Okay, we are out of time. So let's thank Junpak from FuriosaAI.
Thank you. Thank you. All right, thank you.